Hey math fans, Alex here. Last lecture we talked a lot about the natural numbers, and I kind of told you a little bit of a lie, right? I told you that the natural numbers consist of numbers like 1, 2, 3, and then I just kind of did ... Whereas the symbols that you see before you came as a result of many different civilizations interacting, and ultimately it's the result of what's called the Hindu-Arabic numerals. However, you might be, upon first glance, tempted to say that since there are infinitely many natural numbers, do we need infinitely many symbols? Well, no, that would be ridiculous. We don't want a symbol to represent a million and then another symbol to represent 1,000,001. That would be too much to memorize and our brains couldn't handle it. And so there's a little bit of a lie when there are numbers that exist that look like this. So where does that come from? Notice that I have a 1 and a 0. Well, 0 is not even a natural number, so maybe we should first include it in the natural numbers. But moreover, how do we have this system of numbers that we use in our everyday lives? So before I talk about that, I really want to talk about a couple of civilizations and their roles. So a lot of civilizations made a finite number of symbols, and they used additive notation. And what that means, just to give you an example of something you might be familiar with, would be something like the Romans. Okay, so Roman numerals, for example, might have a number like, CXVII. And what that means is C for century. Okay, so that would be 100, and then X is 10. And then V is 5, and then each of the I's represent 1 each. Okay, so you have 1, and then this is another 1. And since the numbers are decreasing in value, or at least they're non-increasing, that means we actually combine these together to form 117. Okay, so anytime you wanted a number, you could represent it using finite numbers of symbols. And it turns out that there are other civilizations that did things similar. Okay, the Greeks did something kind of similar to this. The Egyptians, they represented things additively. And, well, that kind of works sometimes, but which symbols do we use, right? And so C, X, V, and II are kind of difficult to remember. And then what if you want even larger numbers? What if I wanted to represent, say, 1,000,000? You're going to have to just invent a new symbol that represents that. And so that doesn't really work. Plus, the flaw to Roman numerals is there's subtractive notation as well. So, for example, if you have like a small number and then a big number right next to it, okay, so this represents, of course, 1. Okay, so this is 1 and this is 5. Well, that was the symbol to actually take the small number from the big number, and so this is 4. Although if you actually look at grandfather clocks, you will almost never see this. They will always choose to represent it with 4 eyes, which is very strange because that's the entire purpose of this notation, to avoid such stains on the eye, I guess. And so that leads to a natural problem. Is there a better way to represent numbers? And I claim that there is. And to motivate this, I'm going to use a pedagogical tool invented by James Tanton, okay, British math educator, called the exploding dots paradigm. And I'm going to link his videos and his playlist in my videos so you can see them. So please check it out. I'm only going to give you the highlights just so we can kind of understand the basics. Here's how it works, though. I'm going to invent something called a 10-1 machine, and you'll see why it's called a 10-1 machine very shortly. But what I'm going to do is it's going to amount to a box, and in that box there are going to be various sections. Maybe we'll just start by having 3 sections, and the only rule to the 10-1 machine, we're going to have dots in here, the only rule is that anytime you have 10 dots, that is going to transition and explode to form 1 dot in the box to the left. That's why it's 10 and then 1. So let me give you an example. Let's suppose that we have, 9 dots. And then, well, 9 is a symbol right, we understand that that symbol means that we have this many dots, and we can just count them out, of course. But then I choose to increase 9. Let's say instead of 9, now I have one more than that. And so what does that mean if I add another dot? Well, if I add another dot, then according to our rules for the 10-1 machine, we get an explosion. And I'm not going to be as enthusiastic as James probably, but this explosion is going to essentially get rid of all of these dots, and it's going to form a dot to the box on the left. And so that is why, if you take a look very closely, there is one dot here, and there are 0 dots right there. So it looks like the symbol 1, 0 is adequate to represent what we think of as 10 dots, where the word 10, I'm being very careful, means one more than 9. Okay, so again, this is a notation that a lot of people take for granted, and this kind of explains what that means. And of course, if I wanted to add a couple more dots, let's say I wanted to represent 13, well then I already have 10, and so I just have to add 3 more dots. Where am I going to add those to? Well, I have to add them in my rightmost box. Now, you'll hear some educators talk about this as place value, which honestly is kind of a stupid name for it. But I suppose that it's the same general premise as this, where each box has a different number of dots that has a value. Okay? And so we can observe a couple things about this. So for example, let's suppose that I actually wanted to represent the number 374. But of course, that was a bad, I shouldn't have said that. 300? What is 100? I don't know what that is. So really this is just 374. And what that means is I'm going to have 3 dots here. I'm going to have 7 dots here. And I'm going to have 4 dots there. And that was the result of many such explosions. So dots wouldn't exist here in this middle box unless there were 10 dots in the rightmost box that exploded. So in a way, what we can kind of say here is this rightmost box has the value 1. And I'm going to choose to write 1 in kind of a peculiar way. I'm going to write it as a 10 with an exponent of 0. But all you need to know is I'm telling you that that's equal to 1. So each of those dots has an intrinsic value of 1. So if I wanted to represent one more than this, like 375, then I would add one more dot to the rightmost box. Okay? And so note that in the middle column, all of those dots had to come as a result of the explosion of 10 dots to the box on the right. And so each of those dots, in a way, is worth 10. They're worth 10 times as much as the right box. And so I can choose to represent this as 10 to the first, which, remember from the last lecture, means that I want 1 copy of 10. So that's really just 10. And so each of these dots to the leftmost box had to result from an explosion of all the dots in the middle box. So each of these dots would be worth 10 times more than the dots to the box to the right. So that's going to be 10 to the second power, meaning I want 2 copies of 10, which combine to give you 100. So hopefully this looks a little familiar. Maybe in grade school you messed around with these like big 100 sheets, and then you have little 10 sheets, and then you have the individual cubes or the 1 sheets, and then you essentially manipulated that to get various numbers. But I want you to notice something else. I can write this number as a combination. I can write it as a combination of 10 squared, 10 to the first, and 10 to the 0. How can I do that? Well, I can write that 374, or I guess 374, is really 3 of this. So it's 3 10 squareds plus 7 10 to the firsts and 4 10 to the 0th powers. Okay? And it turns out that I can generalize this in ways that you might not expect. So let me just point out a couple of observations about this, okay? So representing this number in that way, I have a couple of key observations that I want to make. Number one is I can write any number. I can write any number that you can think of as some number of copies of 10 to the 0, 10 to the first, 10 squared, and so on and so forth. I can just continue to increase my exponent right here, and I can always write every single number as some number of copies of all these, all added together. And hopefully that's very, very clear from the picture, right? Any number of dots, I'm going to have explosions take place, but that doesn't really matter. They have to fit in those boxes. And so this is really the first observation, is that any number of dots is going to essentially fit in boxes. But then we get another observation that's a little bit cool. The observation is that I can actually write this as some number of copies of, 10 to all these different powers. But the second observation is the number of copies that I get of each, we'll say 10 to the n, can always be found to be what? Well, it can always be found to be between 0 and 9. What do I mean by that? I mean that for any number, you pick any number, I can always find a way to combine the different number of copies of 10 to the 0, 10 to the 1, 10 squared, 10 cubed. I can always find a way to do that to where the number of copies never exceeds 9. And that's where the whole exploding part of the exploding dots paradigm comes in. Why? Well, because anytime I have more than 9 copies of something, that 10 or above always goes to the next box. And that would form a number of copies of the next exponent up. Okay? And this becomes apparent whenever I perform other operations. Okay? So as an example, let's suppose that I wanted to add 2 numbers together. And honestly, let me do 2 things at once. So this is an example. So this is going to be addition. I'll teach you how to add. Instead of a 10-1 machine, I'm actually going to do maybe a 3-1 machine. That should be fine. That just means that I'm going to have the symbol 0, the symbol 1, the symbol 2. But anytime I have 3, those 3 dots explode, and I have a new dot in the next box. Okay, so let's suppose that I wanted to do the operation 2, 1, 2, and I wanted to add that to 1, 0, 2. I can't call this 200, okay? 100 does not exist in a 3-1 world. But let's just perform this operation, and I'll kind of show you what's going on. Okay, so what I'll have is some number of boxes. And let's first represent 212 as, well, it's going to be 2 dots here, 1 dot here, and 2 dots here. Now 102, as I add that, well, what's going to happen? Well, I'm going to add 1 dot over here, and you might think there are some explosions that will happen. We'll get to that in just a second. I'll have no dots there, and I'll have 2 dots over here. Let's work right to left. So over here, I'm going to have how many explosions? Well, I'm going to have 1 explosion that's going to get rid of these 3 dots, and it's going to form a new dot to the left. I'm also going to have another explosion where all of these 3 dots are going to explode, right? and that's going to form a dot to the left of that. And so what we really get is the number 1, 0, 2, and 1. And indeed, in a 3-1 machine, 212 plus 102 is equal to 1021. As strange as that is, that's what you get when you only use that many symbols. Okay? We get a seemingly really large number. Now, what's happening behind the scenes? Well, remember, according to our observations here, I can write any number as copies of, well, we don't have a 10-1 machine, we have a 3-1 machine. So I can represent any number as some number of 3 to the zeros, plus some number of 3 to the 1, plus some number of 3 to the second, and so on, where each of those number of copies has to be between 0 and 2. So let's see that in action. So with the number 212, let's just do the addition again and let's represent it. So 212 can be represented as follows. So I'm going to have, let's see. Well, this is going to represent 3 to the 0, which remember is really just 1. This is going to be 3 times that, because each of these dots is 3 times the previous one. So this is going to be 3 to the first. This is going to be 3 to the second. And this is going to be 3 to the third. So the number 212, if you will remember, there were 2 dots here, 1 dot here, 2 dots there, which means I can represent 212 as 2 copies of 3 to the second, plus 1 copy of 3 to the first, and 2 copies of 3 to the 0. Likewise, I have 102, and I can represent that in much the same way. I have 1 copy of 3 to the second. I have 0 copies of 3 to the first. I'm still going to write it like that, though. You'll see why in a second. And I'll have 2 copies of 3 to the 0. Now, what happens when I want to add 212 and 102? Well, if I want to add these two numbers, I can do that just fine because we talked about the distributive property. Okay, and so what I'll have is that with these groups, for example, I can factor out the 3 squared. And what I end up with is 2 plus 1. So I have 2 plus 1 numbers of 3 squared plus 1 plus 0 copies of 3 to the first plus 2 copies of 3 to the 0. Okay, so that was observation number 1, that any number, even if you add 2 numbers and you get a third number, that third number I can always write as some sort of combination of 3 to the zeros, 3 to the first, 3 squared, 3 to the third. It's just that everything past 3 squared, I'm going to have 0 copies of it. But I can still technically write that if I wanted to. I could still technically write 0, 3 cubes, and so on, but I don't need to do that. Okay. Now, the second observation, which said that every number of copies, I can always find a way to make the number of copies of each of these between 0 and 2. So it's always going to be 1 less than the type of machine you're in. Why is that the case? Well, let's play around with this a little bit more. So this is going to equal, what is it going to equal? Well, this is going to be 3, which is like that. This is going to be 1, so I'll just write it like that. This is going to be 4, okay? And so I'm going to write 4 in kind of a funny way. You're going to laugh at me, but stick with me. So we know that this is equal to 4, but remember I can choose to represent this as 1 plus 1 plus 1 plus 1, and then the associative rule says I can group them however I want it. I'm going to choose to write this as 3 plus 1. And you'll see why in just a second. Now watch what happens, okay? This 3 times 3 squared gets me 3 cubed. How many 3 cubes? Well, just 1. After that, I don't have any 3 squareds anymore because they all exploded. So I really am going to write 0, 3 squareds. And then I have this situation, okay, where this is going to be 1, 3 to the first. And then after I use the distributive law, this 3 to the 0 is going to distribute to both of these terms. So what I'm going to end up with is, let's see, this is going to be 3 to the zeros plus 1, 3 to the zeros. Now what's happening here? Well, the thing that's happening is I have 1 copy of 3 to the third. I have 0 copies of 3 squared. How many copies of 3 to the first do I have? I argue that I actually have 2. Because this thing right here, 3 to the first times 3 to the 0, that's 3 to the first. So I have 1 copy there and I have 1 copy there. So I'm going to have 2 copies of 3 to the first. And then I have 1 copy of 3 to the 0. So look at that. Any number, I guarantee you I can always represent that as some number of 3 to the zeros, some number of 3 to the first, some number of 3 to the second, some number of 3 to the third, some number of 3 to the fourths, and so on and so forth, where the number of those that I have will always be 0, 1, or 2. And that's for a 3-1 machine. And you can generalize this, of course, but hopefully it's obvious from the model, right, the dot model. And it's also what's really happening is the distributive law. Anytime I have a number over that, what I can do is I can always write that as 3 plus something less than 3. Or at least I can write it as some number of copies of 3 plus something else. What I'm really doing is actually doing division, right? Because I'm finding out how many, like what's the largest number of copies of 3 that I could have right here before stuff goes wrong. But we'll talk about that in a second, okay? So that's how you would add any two numbers. And so before I go any further and talk about subtraction, let me talk about a couple of definitions, okay? And for some reason, this was never really taught to me, and I just kind of made the realization when I was writing the notes for this. But let's kind of define something that you might find something somewhat interesting. Okay, so for our, I'll just stick with a 3-1 machine because we did so much with it. For a 3-1 machine, I think, you know, those of you that have some experience with this might kind of know secretly behind the scenes what this is. This is called our base. Why is it called our base? Well, remember that with exponents, the way that I defined it, if I have 3 to the third or something like that, then this was called our, okay, that was a horrible choice. Let's do that, 3 to the 4. And so 3 was our base, and 4 was the number of times I'm multiplying. And so we call that the exponent. Okay? Now, here's what I'm going to define for you. So I'm going to define something called a basis. And a basis is going to be an infinite set. That's what it's going to be. However, it's going to be somewhat of an interesting infinite set. It's going to consist of bases raised to, it's going to consist of the base being raised to every single natural number power, and yes, I am including zeros and natural numbers. So it's going to be 3 to the 0, 3 to the first, 3 squared, 3 to the third, and so on and so forth. Every single natural number exponent with 3, with that specific 3 as the base. Okay, so obviously for each machine, a 3-1 machine is going to have one basis, a 10-1 machine is going to have a different basis. It's only going to have one basis though. I mean, you could technically probably have different bases, but we're not going to get into it. We'll just say that this is the only basis. And what I have is, you can call it a theorem if you want, So we'll call it a theorem. And the theorem is, okay, so I can state the following theorem about what we just kind of observed, okay? And so what the theorem is going to say is that for a given base, I have to pick a base and stick with it. So maybe I have a 3-1 machine, I'm working in base 3, or a 10-1 machine, and then that's base 10. So for that base, every number can be expressed as the sum of numbers of copies of elements in the basis. Okay, so I have 5 3 to the firsts, maybe I have 7 3 squareds, and I have 3 3 to the thirds, whatever. Okay, I can always express a number as the sum of numbers of copies of elements in the basis. And oh, by the way, if you think this is a little bit weird wording, the sum, that means I'm adding together copies of each of these elements. There is a mathematical word for that, and the mathematical word is a linear combination. So if you've ever heard a linear combination, it means a combination. That means I'm picking this thing here and that thing here and that thing here, but then the linear comes from the number of copies. Okay, so this word goes with the number of copies, and this combination means I'm summing, or I'm combining or adding all of those together. Okay, and so I can actually put restrictions on these numbers of copies, because the numbers of copies, remember, I mean, it must be a natural number, right? I can't have like a -5 number of copies unless we're talking about the integers, but that's a separate story. So they have to be a natural number, and it has to be at most one less than the base. I can always find some way of expressing that. Now, the stuff in black, I don't really need to prove that because it's just obvious from the exploding dots model, right? And so, I mean, any kind of number, I can really just think of that as the representation of that linear combination of elements in the basis. The stuff in blue, we'll prove that a little bit later, or I might just kind of sketch out kind of the argument. Okay, but it does have to do with division, which I haven't formally defined yet. Okay, let's do another example. Let's do some subtraction this time. Okay, and so let's do. So this is subtraction now. And so with subtraction, maybe this time I actually do a 2-1 machine. So I'm working in base 2, and if you know what base 2 is, there's actually a name for that. It's binary, which is what computers use. So we'll get some insight as to how computers work. And so for this 2-1 machine, our base is 2, which means we'll have dots here representing 2 to the 0, dots here are 2 to the first, dots here are 2 squared, dots here are 2 cubed. And so those are all part of the basis. All right? And so what I want to do, the problem is to take 1, 1, 0, 1, because remember, since I only have base 2, I only have 2 symbols to represent all the numbers. I have 0 and I have 1. 2 doesn't exist. But anytime I have 2 dots, which is represented, well, just by 2 dots, those explode into 1 dot. So I want to take this minus 1, 0, 1, 1. Okay, and of course, remember that what that really means is I'm really adding, this is the lazy notation, but I'm really adding this negative number. Okay? Well, we can actually figure that out pretty easily using our 2-1 machine. So let's represent 1, 1, 0, 1. So it's going to be, let's see, 1, 1, 0, 1. And this time, to denote the negative number, since I am subtracting, I'm actually going to use a different color dot. Yay! So let's use a red dot to represent 1, 0, 1, 1. Okay, so I have 1, 0, 1, 1. And you might think that some explosions are going to happen, and they are, but the only explosions that produce a dot in the box to the left are the ones with the same colored dots. Okay, you all remember from last lecture that blue and red dots completely annihilate each other, like electrons and anti-electrons. So before any exploding dots produce more dots, what we really have is this completely cancels, and this completely cancels, and I just have one blue dot and I have one red dot. I don't like that so much, right? I don't like having red dots. So what I can really think about doing is I can really think about moving this dot over to the right. But then how many dots would I have to draw? Well, this is like pre-explosion. So what I really have is that I can erase this blue dot and move it over to the right as 2 dots. Now, normally, yes, those 2 dots would explode and move back to the left. But before that happens, I really have that the blue and the red dots annihilate each other. So I really just have that. And that is my answer. Okay, so it looks like 1101 minus 1011 is going to produce the number 10, which is not 10. All right, let's see what's happening behind the scenes. So I can again represent each of these numbers as follows. So I could represent 1101 as 1 instance of 2 cubed plus 1 instance of 2 squared plus 0 instances of 2 to the first plus 1 instance of 2 to the 0. Okay. And what I really have is I really am adding the inverse to this number. So all I'm going to do is I'm just going to make everything negative. Okay, so I have minus 1 copies of 2 cubed, and then minus 0 of 2 squared, and then minus 1 of 2 to the first, and minus 1 of 2 to the 0. And when I add all of those together, I'm going to have some factoring, okay, using the distributive law, but then I'm going to have, if I combine this, I'm going to have, let's see, 1 minus 1 copies of 2 cubed plus 1 minus 0 copies of 2 squared plus 0 minus 1 copies of 2 to the first plus 1 minus 1 copies of 2 to the 0. Okay, well, clearly this is 0, this is 0, so those cancel, and then I'm left with this. Okay, well, the negative 1 kind of presents to be a little bit of a problem, so I'm going to do something a bit strange, and I'm going to take one of these copies of 2, and I'm going to distribute that. Okay, so what I'm really doing is I'm using a bunch of different arithmetic properties. So what I'm really doing is I'm writing 2 as 2 times 2. Or really, I'm just lobbing off 1 copy of this. If this were 2 cubed, this would be 2 times 2 squared, and so on and so forth. And then I'm distributing this thing to, I mean, both of those terms in some sort of sense. Okay, and so what I end up with is I end up with 2 copies of 2 to the first minus 1 copy of 2 to the first. And so I can always do that if I have something that's non-zero right here. I can always distribute one of those 2's. And now look, now I don't have a negative anymore because the 2 to the first distributes, and that's going to be 2 minus 1 2 to the first, which is just 1 copy of 2 to the first. And so it looks like I get 2 to the first, which is exactly what we got here, which is exactly the number 10. So what did we learn in this video? Well, we learned that many civilizations have tried to represent big numbers by using a finite number of symbols. But this whole idea of like having to do a bunch of work by adding them is really cumbersome. And so the Hindu-Arabic system has the advantage to where all of these finite symbols are really in one basis. And we talked about what a basis is. And pictorially can be represented using James Tanton's exploding dots method, where in order to represent a number, you just put a bunch of dots with the rule that whatever the base is, when you reach that number of dots, then that combines into 1 dot in the next box to the left. And so we can write any of those numbers as some number of copies of elements in the basis, which we've illustrated a couple of different times, and those number of copies have to be strictly less than the base itself. Anytime you have something more than the base, you can lop off extra copies, and you can always express numbers having those special properties. And we also did examples involving addition and subtraction, and we did multiple different bases. In the next video, I'm going to teach you how to convert between one base and another. So all the examples in this video involved some number of dots in one base and some number of dots in the same base, and we combined them using addition and subtraction. And in theory, and with multiplication, I want you to think about how that would work. It would work in the exact same way. It would just be repeated addition. Okay, but I'm going to show you how to go from, say, base 2 to base 3. And it's going to involve division, so we're going to formally-ish define that. Hope to see you in the next video, and have a great rest of your day.